All right, let's jump right into it. Today, we're going to tackle a massive question in the world of AI, something that every single person building these incredible tools has to deal with. So you've put in the hours, you've built this model, and on paper, it looks amazing. But how do you know it's going to work out there in the real world with data it's never seen before? How do we get past just building a model and start building one we can really, truly trust? That's the problem we're going to solve today. Okay, so the biggest villain in our story, the thing that destroys trust, is this concept called overfitting. This is what happens when your model gets, well, a little too smart for its own good. It doesn't actually learn the rules of the game. It just memorizes the answers to the test you gave it. And just like that student who can recite the textbook but can't think for themselves, an overfitted model will fail, and fail spectacularly the second it sees something new. So, how do we fight this? How do we stop our models from cheating? We use the absolute golden rule of machine learning. We split our data. You can think of this as the scientific method for AI. Before we write a single line of code for the model itself, we set up a system for an honest, fair evaluation. This whole thing works by splitting our data into 3 different piles. First up, you've got the training set. This is the textbook. It's what our model gets to study. Then there's the validation set. This is like a practice quiz. We use it to check in, to tweak the model, and to make sure it's actually learning, not just memorizing. And finally, the most important part, the test set. This is the final exam. We lock it away, and we only look at it once, at the very end, to get a truly unbiased grade on how our model will perform out in the wild. So what does this split actually look like? Well, a super common recipe is something like this. You use the biggest chunk, about 70% of your data, for the training, for the textbook. Then you set aside 15% for those practice quizzes. That's your validation set. And that leaves the final 15% for the final exam, the test set. The whole idea is to have enough data to learn the patterns, but also enough left over to honestly check your work and get a final grade you can count on. Okay, so our data is split. It's ready for a fair fight. Now we actually need a model to do the work. Let's start with a real classic, an absolute workhorse in machine learning, logistic regression. Now, here's a little twist. Despite having regression right there in the name, this tool is actually for classification. It's designed to answer questions that have a yes or no kind of outcome. Things like, will this customer buy our product or not? Or is this email spam, or is it legitimate? And it does this by giving us a probability. The magic behind logistic regression is that it fits this really elegant S-shaped curve to your data. What this curve does is pretty cool. It lets the model take any input like a customer's age or how much they've spent in the past and map it directly to a probability, like the exact chance that they're going to click buy. And this is a huge deal. It means you get more than a simple yes or no. For a bank, it won't just say, this person will default. It'll say, there is a 72% chance this person will default. That specific number, that probability, is incredibly powerful. It's something a human can look at and make a real nuanced decision with. But what if you don't really need a probability? What if you just need a decision? Well, our second tool, the support vector machine, or SVM, comes at this from a totally different, much more geometric point of view. Unlike logistic regression, an SVM doesn't care about probability at all. Its one and only job is to find the single best dividing line, the best boundary to separate 2 groups of data. It's not trying to figure out the chance of being in one group or the other. It's trying to find the clearest separation between them. I love this analogy. To really get it, just picture your data points as houses scattered across a map, belonging to 2 different neighborhoods. An SVM's job is to draw the widest possible street it can between those 2 neighborhoods. It wants to create the maximum amount of empty space, the biggest separation. And the houses right on the edge of that street, those are your support vectors. They define the boundary. So let's go back to our bank loan. You give that same applicant's info to an SVM. What does it spit out? Not a percentage. It gives you a direct, decisive answer. Yes, default. Boom. That's it. It's a classifier, pure and simple. All right. So we have the predictor,
logistic regression, that gives us those juicy probabilities. And we have the divider, the SVM, that just draws a hard line in the sand. They're both awesome tools. So how in the world do you choose which one to use?
It really just boils down to what you need your model to do. If you need a probability, if that 72% chance is important, and you need to be able to explain why the model made its decision, logistic regression is your best friend. It's fast, it scales well, and it's super easy to interpret. But if all you care about is getting the most accurate yes or no you can, and you're not as worried about the why, an SVM can be a powerhouse, especially when your dataset isn't gigantic.
Okay, one quick pro tip. What happens when your dataset is tiny? That 70-15-15 split can actually be risky, right? You might not leave enough data in your training set for the model to learn anything. So in that case, we use a much smarter technique called n-fold cross-validation. You just split your data into, say, 5 chunks, or folds. Then you train the model 5 separate times, and each time you use a different chunk for your practice quiz. This lets you use every single piece of your precious data and gives you a way more reliable idea of how good your model actually is.
So let's just do a super quick recap, a little cheat sheet. To teach your model, you use the training set. To tune it, compare it, and give it practice quizzes, you use the validation set. For that final honest-to-goodness grade, you use the test set, and you only use it once. And if you're working with a small dataset, cross-validation is your absolute best friend.
You know, when you peel it all back, this whole process, all this splitting and testing, it all comes down to this one simple core idea. Our goal isn't just to build a cool model. The goal is to build a model that you can actually trust to do its job out in the real world. This isn't just a game. This whole system is designed to build something you can confidently use to solve real problems.
By following this blueprint, you're not just building powerful models, you're building reliable and trustworthy ones. So the only question left is, now that you have the framework, what problem are you going to solve first? Thanks for tuning in to The Explainer.